Hello, welcome to this video produced as part of the Further Maths Support Programme's material for A-Level Maths and Further Maths. This one focuses on the basic principles of using the work-energy idea in problems. What is the work-energy principle then? Well, basically it's that work done is equal to change in kinetic energy. It's used when there are non-conservative forces doing work. That is, forces which don't have a potential term, like potential energy for gravity or potential energy for a stretched string. And we can take account of work done by using the principle work done is equal to change in energy. So the left hand side here is the work done by friction or driving force or some other force of that nature. On the right hand side we keep an account of the change in energy under the three categories: gravitational potential energy, kinetic energy and elastic potential energy. So let's look at this in the context of a simple problem. An object of mass 0.5 kilograms is attached to one end of a light spring of natural length 40 centimeters. Caution, that will have to become 0.4 meters. And modulus of elasticity 180 newtons, no problem there. The other end is attached to a fixed point O on a rough horizontal table. Rough horizontal table. The horizontal means that gravity won't do any work, and nor will any reaction force, so long as the particle or the object stays on the table, but there will be a friction. The coefficient of friction is 0.3. The object rests on the table as pulled away from O to a distance of 0.5 meters. The object is then released from rest. Calculate its speed at the point when the string becomes slack. It's a kind of table-based catapult with only one string, but it's the same idea. Well, we'll need for this the elastic potential energy, lambda x squared over 2L. So let's sort out what the various parameters there are. Lambda from the question is 180. The natural length we agreed would have to be 0.4. The extension, careful here, it's 0.4 up to 0.5, so the extension is 0.1. And the coefficient of friction is 0.3. Now let's look at that represented in a diagram. First of all, the initial situation. I've shown there the stretch in the string of 0.1, the mass and the velocity at the beginning. And here we are, the velocity at the end when the string is unstretched and it's acquired a velocity v. So on this page I've summarised what I had on the last page, but I've included the two diagrams in one. There's that formula again. Now let's look at the force diagram. There's a tension in the string, that's what causes all the action, and there'll also be a friction force F in the opposite direction. The weight shown as 0.5 g, and there'll be an equal and opposite reaction of 0.5 g. I've saved myself a line by using the R as a point of reference, yes, but indicating that we already know that that's 0.5 g. The friction will be expressed in terms of the normal reaction. That's why we have to do that calculation first. As I've already said, as regards work, the 0.5 g doesn't do any because it's perpendicular to the motion's direction, nor does the reaction. The friction certainly does, and that isn't a conservative force, so we'll need to calculate the work done directly, but the tension can be accounted for by the change in elastic potential energy. So first we express the friction in terms of the reaction. It will be just the coefficient of friction times the reaction because it's sliding, so we get the maximum possible friction. The work energy principle tells us that the work done is equal to the new energy by the minus the old energy, so our consequent equation has on the left the force F, which we already know is 0.3 times 0.5 g, times the displacement. Notice I say displacement rather than distance, because the displacement in this sense is in the opposite direction to the force, so hence it has to be included with a minus. On the right is the energy audit. Now if we take the energy finally first, we have the kinetic energy and a slack string, so it's simply kinetic energy. There's the mass and there's the usual half and v squared. And if we now work on the original energy, there's no kinetic energy because the velocity is 0, but there is the energy of the stretched string. So there's our lambda x squared over 2 times L. Now that equation solves the problem, because we're trying to find V. It's a matter of getting V equals out of it. So that's the result that we'll get. It's not a dead trivial step, isn't that? You're going to have to move the term, this term, to the other side, and in the process simplify it. The top 180 times 0.1 squared is just 1.8. The bottom is 0.8. So that's where this term comes from. This one simplified, 0.3 times 0.5, 0.15, and then you get 0.015, and it's got the minus sign. That's where that comes from. So essentially, that square bracket is the right-hand side of this, the left-hand side of this equation, with ending with equals half times 0.5 v squared. Then we'll need to multiply by 4 to make it v squared. So there's our 4, and as a result, we simply work out that calculation using the value of 9.8, and the answer is 2.90. So there's my sentence in context giving the answer with the units. Now let's look at a second problem, which involves potential energy, gravitational potential energy this time. We've got a particle of mass 0.8 kilograms, and it's attached to string, natural length 0.5 meters, elasticity 40 newtons, no problems with the units so far. It's on an inclined plane, inclined at 30 degrees, and there's a fixed point A which anchors the string at one end. The object's held at A and released, so then it slides down the slope. And P comes to rest instantaneously as the string starts to stretch. Eventually the force of the string will bring the particle to a stop. It will carry on afterwards that in reverse direction, yet of course, but that's what we're asked for, or that's what we're told. We're told the distance it travels to get to that point of instantaneous rest, and our objective is to find the coefficient of friction. So we will begin by summarizing that the problem on the left is exactly as we've just said. I've just taken up less space. We'll need to use our usual formula for elastic potential energy and extract from the question the various parameters. So lambda is given as 40. The natural length is 0.5. We're told that it's 0.7 below A along the slope, that is, when it finishes, which means there's an extension of 0.2, and mu is what we're trying to find. So there's our summary of the information. We have zero velocity at the start, it starts from rest, zero velocity at the end because the 0.7 meters is the point at which it comes to a momentary rest. The distance travelled is 0.7, so that's my attempt to summarise the information without having to repeatedly read the question. Now the force diagram, as usual, there's a gap between the particle and the plane so that it's clear that the forces that we show act on the particle. We have a normal reaction, as always. We have a friction, and we have the tension in the string. That's when it's in motion between A and B. For the first part of the motion, the first half a meter, the tension will be zero because the string is still slack. Now, how are we going to analyse this? We're going to find out what R is by resolving perpendicular to the plane, and then we're going to find out what F is by saying that F will be the coefficient of friction times R. So there's the picture again, nothing new there. We start off by resolving. We're going to be resolving along this line, this line, perpendicular to the plane, and there'll be an angle of 30 degrees in here from the diagram above. So it will be 0.8 g cos 30 that matches the R. Now we take the friction, it's just the limiting friction, that is the coefficient of friction times R. So now we use the work-energy principle, so we have to do work done from the appropriate force. Now in the force diagram, R does no work because it's at right angles to the slope. 0.8 g does, but we can account for that by the change in potential energy. The tension does, but we can account for that by the change in stretched energy, the energy in the stretched string. And the friction, however, isn't a conservative force, so we'll need to calculate that one directly. So there's our equation. Here's the friction. Now that's pointing up the plane and the motion is down the plane 0.7 meters, so hence the minus sign. The right hand side has the final energy. Now that's the stretched energy, because at that stage the string has stretched by 0.2 meters. So you have the lambda times the x squared over the 2 times the L, and you subtract from that the original energy. Now I'm taking here the potential energy level 0 as at B, so there's no potential energy in the final analysis, but there is in the initial analysis, and that will correspond to the force of gravity 0.8 g and the distance upwards that's moved on this diagram here. So that will be 0.7 times the sine of 30, and that's where that second term comes from. It's worth noting that there's an alternative way of interpreting this. We could take the whole of this as the final energy, in which that's regarding the 0 level as at A, because in that case you'd have the same stretched energy, but since B is below A, there'll be a negative contribution from potential energy, in which case, looking at it that way, what you see is the energy at the end, and the initial energy will be 0. No stretched energy, no potential energy. Comes to the same thing. Okay, now when we work this out, a bit of simplification first. 0.7 times 0.8 gives us 0.56, so we have 0.56 times mu times g and a cos 30. And on the right hand side that will simplify to a 40 times 0.04, which is 1.6. The 2 times 0.5 doesn't tell us anything at all, that's just 1, and then minus, there'll be the same 0.56 times g times sine 30. So that's what that equation amounts to. If you keep that in mind till we move to the next explanation, you can see now then that that equation will rearrange to mu equals simply by dividing by what was 0.56 g cos 30. There it is underneath. And on the top you've got the 1.6 that came from this term, and the other term is the one on the left, 0.56 times 0.98 times a half. Note sine 30 is a half, cos 30 is root 3 over 2. Why have these two terms turned round? Because of that minus sign there. So that figure, that expression is the calculation to do, and the answer is 0.2407, etc. I'm too lazy to write more than 4 figures from a calculator, but I imply there are more. And then finally I've rounded it to give the coefficient of friction as 0.241 to 3 decimal places. Well, that brings to the end that presentation. The next one is on using vectors to calculate work done.